This is the second video in a series about the Quine-McCluskey logic minimization algorithm. In this video, we will explore how to proceed once we have obtained all of the prime implicants from a Boolean function. Our goal is now to pick a minimal subset of the prime implicants in order to fully cover all of the minterms of our function. Once again, I will illustrate the steps using a K-map. So here we have the results from the last video, where we had a function given as a summation of minterms and don't care terms. We then found the prime implicants using the tabular method. And now we're going to construct what's called the implicant table. This is what the implicant table is going to look like. It has all of our minterms over here for the rows, and I've denoted them with their corresponding numbers from the sum of minterms expression. And we have the prime implicants that we found on the columns from this chart over here. Notice that the minterms do not include the don't care terms anymore, because we don't need to cover them in order to realize our function. We only have to cover the minterms, the ones, in our logic table. So from here, we're going to fill in this chart by seeing which minterms a given prime implicant covers. So what we look at is the expression of the prime implicant. And so this first one is 0 dash dash 0, or a bar d bar. And so we look for corresponding minterms that have that pattern, 0 dash dash 0. So this one fits. It doesn't matter what is in the dash places, all that matters is what is in the places that are denoted by a 0 or a 1. Do we have any other terms like that? So 0, 1, 0, 1 does not fit because of this 1. 0, 1, 1, 0, that works. So we place a 1 here as well. None of the rest start with a 0, so we know that none of these are going to work. And so we move on and we look at the next one, dash 1, dash 0. This first one does not fit. This one, dash 1, dash 0, no, because of this 1 at the end. Dash 1, dash 0, yes, this one works. So we can place a 1 here. And we keep looking and we see that also these two are going to work. And so we fill in the table using these rules. And we get this. Now, this basically gives us the same exact information as a K-map with all of these prime implicants circled, which is something I showed in the previous video. Because we now know that this term is going to cover both of these minterms. Both of these minterms are going to be in the encirclement made by a bar d bar on a K-map. Likewise with b d bar, 3 minterms are going to be covered by that. And so on for all of these. So basically we have the same exact information as we would in a K-map. Now, the question is, how do we simplify this in order to get an optimal solution? So let's take a look at the possible minimization steps. Now, in order to select a minimal subset of prime implicants, we have to make sure that all of our minterms are covered. What that implies in this table is that we need there to be at least a single 1 in every single row. That means that a given prime implicant is encapsulating every single minterm. So we can see that there is a 1 in every single row, and this is guaranteed just by the formulation of the problem, but there are oftentimes more than 1 in a given row. And so we want to pick only, again, a minimal subset of the prime implicants. And the first operation to do that is to eliminate the essential columns. A column is essential if it contains a row which is covered by only 1, 1. So for example, this row right here has only 1, 1, and it's covered by this column which is essential. So we can denote that right here. And there is another essential column here, which is the second one, because this row has only 1, 1, and it's in this column. When we do this, we can also eliminate not just these columns, but also all of the corresponding minterms with ones in their row, because we have covered them with this. So in other words, we get rid of this row, we get rid of this row because there is a 1 in here, even though this wasn't the only one in this row. Since we're including this prime implicant, that means we are covering this row as well because it does have a 1 in it. Of course, we eliminate this one since that was the only one. And we also eliminate this one. Again, even though it has more than one 1 in the row, it's already being covered by this prime implicant. And so now we say that we include B D bar and A bar B C bar in our solution set, and we redraw the table without these selected prime implicants and the corresponding minterms, which we have crossed out here. So on a K-map, what does this look like? The essential columns covered the following minterms. So this one over here covers 0, 1, 0, 1. Well, 0, 1, 0, 1, that's this term right here. And this essential one covers 1, 1, 0, 0. 1, 1, 0, 0, that's this one right here. And the prime implicants that do so, this first one over here was A bar, B, C bar. That's this encirclement here. And the other one, B D bar, is this one over here. We can see that both of these prime implicants are essential because they cover a minterm which is not covered by any other prime implicant. If we look at all of our other prime implicants, none of them are going to cover these two terms other than these two prime implicants. Therefore, they have to be in our solution. So we say that our solution contains B D bar and A bar B C bar, and we simplify our table by getting rid of the corresponding columns and the rows which they cover. And so for A bar B C bar, you can see that it covers just one minterm, which is this one, and a don't care, which we don't have to cover. But this term, B D bar, covers this essential minterm, but also two more. Now these two other ones are covered by other prime implicants. And that can be seen because there is a 1 in another column. It's also covered by A bar D bar for this one, for 0, 1, 1, 0. And 1, 1, 1, 0 is also covered by A, B, C. However, since we know we have to include B D bar because it is the only one that covers this minterm, then we don't have to include the other prime implicants which cover the same minterms that were already covered by this prime implicant. So that's why we're able to simplify this function, and we say that we don't need to cover these two minterms any longer because we know we're covering them by including B D bar. That's why we're able to cross out both columns and the corresponding rows for every place where there is a 1. And this greatly simplifies our table because now we have only 3 rows and 5 columns as opposed to the original 7 rows and 7 columns. The next simplifying technique is going to be to get rid of dominating rows. Now, a row is said to dominate another row if it has all of the ones of another row and maybe more. So for example, here we have a dominating row, specifically this row right here for 1, 1, 1, 0. It has this one and this one at the end, whereas row 1, 1, 0, 0 has only this one corresponding to the same location and nothing else. So this row clearly has all the ones of the previous row and then some. So it is set to dominate it. And we can get rid of dominating rows. So specifically, we're going to get rid of this row. So what does this mean? We can look at these two minterms in our K-map, And it's going to correspond to, for this one, 1110. That's this term over here. And 1100, that's this term right here. And we're saying that we can get rid of this min term for our analysis. So how can we know that? By looking at this dominance relationship between these two rows. So let's look at the prime implicants which correspond to these one locations. The first one is BD bar, so that would be this min term right here. Sorry, this prime implicant right here. And the other one is ABC. So that is going to be right here. ABC. So what this is saying is that we don't have to consider this min term as long as we consider this one, because we know that the prime implicant that covers this min term also covers this min term, so we no longer have to really consider it, because we know it's going to be covered, and therefore we can get rid of some unnecessary prime implicants potentially. See, because we get rid of this row and we get rid of a 1 in the ABC column. If that was the only 1 remaining in this column, well, this whole column would be gone. However, there is still a 1 below it, so it's not completely gone, but we still simplify things because we now know that we no longer have to consider this particular min term individually, and so we can redraw our table without the dominating row. So now our table is going to simplify to 6 rows and 7 columns. We don't know anything about including another term in our solution set like we did before by looking at the essential columns, but we can simplify our table so that maybe other relationships and essential columns can emerge. The last step that we can take in simplifying our implicant table is going to be to eliminate dominated columns, and this is going to get rid of redundant prime implicants. So once again, a dominating relationship between columns is going to be a column which has all the ones of another column and maybe more. So in this case, we can see that we have this column here which dominates the column to its left because it has a 1 in this location just like this one, and a 1 here, whereas this one only has just a single 1. So we can get rid of the dominated column. Remember, we got rid of dominating rows, but dominated columns. So specifically, this column is going to be deleted from this table. So what does that mean on a K-map? Let's look at these two prime implicants. So first, we look at ACD. That's this term right here. And B bar CD. And what we see is that B bar CD is completely redundant, because if we include ACD, well, then we automatically cover the only min term that B bar CD is actually covering. B bar CD also covers a don't care, which we don't have to include. So therefore, if we include ACD, we do not need B bar CD, and therefore it can be eliminated. That's what the dominating relationship between columns tells us. So once again, we can simplify our table. We don't know anything about including a particular term because we need more analysis for that, but we can get rid of a column, so now we reduce this to a 7-row, 6-column table. So that helps with simplifications. And from here on, you just look for more of these relationships. You can do this in a loop. Look for essential columns, then dominating rows, then dominated columns. That'll simplify your table down to a given form, and then you do it again. Look for essential columns, dominating rows, dominated columns. It doesn't have to be in that order, but that's just a simple order to keep track of. So let's look at how all of these operations can simplify our actual example. So just like before, we can see that we have some essential columns here. Specifically, we have this column, and we have this column. And once again, we can eliminate the rows which correspond to ones in this column, in these two columns. And we know that we have to include these terms in our solution. So we know that we have b d bar and a bar b c bar in our solution. Okay, so now we can redraw our table, our much simplified table, which will look like this. So we can fill this in once again just by looking at the corresponding locations of ones in the original table. Everything stays the same, and we get this as our table. And now there are no more essential columns, but we do have some dominance relationships, specifically among the columns. So there are no dominating rows in this case, but there are dominating columns. So the fourth column here dominates its surrounding two columns, since it has a 1 in this location and a 1 below, whereas this one just has this single one, and same thing with the column on the right. So therefore, we can get rid of these two columns. Now these two have a 1 in the same location. They are said to dominate each other. Remember that I said that a column dominates another if it has all the ones and maybe more. So it can have the same number of ones. And so basically we can choose which one of these to eliminate. And so we can eliminate, let's say, this one. So now we don't know that there's going to be any more terms in a solution from this, but we can simplify our table even further. And now our table is going to become this. Once again, we fill it in with the corresponding terms that belong here. And now we're pretty much done, because now we actually have both of these columns as essential. We see that this is the only one in this row, and this one has the only one in this row, and with this one as well. So therefore, both of these columns are essential, and we also cross out their corresponding rows. And we're done. We're done as soon as our table is completely empty. So we know that from this we include two more terms, the ones that were essential. Specifically, we know that a bar, d bar, that's that first one, and a, c, d are going to be in the solution. And furthermore, since now the table has simplified to empty, that means that our solution is complete. We're done. And the solution that we got from this is going to be the set of those essential prime implicants. So that's going to be b d bar, a bar d bar, a bar b c bar, and a c d. This is our solution set. So let's take a look at what this looks like on a K-map. We can draw our prime implicants that we found in our optimal solution on the K-map, and we're going to get this. So we have b d bar, which is right here. We're going to have a bar d bar, which is this term over here. And we're going to have a bar b c bar, which is here. And finally, we have ACD. So you can see that this is an optimal cover of this function, where we have been guaranteed that by following this technique. We can see our original two essential terms over here, which were b d bar and a bar b c bar. And then other terms became essential as we performed eliminations on the table and got it to simplify down to what we finally had, where these two terms became essential with everything else simplifying down due to dominance relationships. In this case, we never had to use row dominance. Everything worked out without it, but that's just another tool to use during the simplification process. So that's really it. In this video, we have seen how to select a minimal optimal subset of prime implicants in order to cover a function using an implicant table and reduction techniques. There is a special case of an implicant table, however, that cannot reduce using any of these techniques. There are no essential columns and no dominance relationships. This case will be explored in the following video.